Oh, yeah. Hi, I'm Marcin. I clicked on the wrong link. There was some invite coming in and like, hey, come join us, answer a bunch of questions, and here I am. So for the listeners, be careful which links are you clicking on. So you might get into a hopefully very interesting show. One thing researchers are busy with is making sure that their words are sounding complex. Like, imagine the first person that got the spam emails. Wow, Korean prince is giving me all this money. Now we think it's funny, proof, but I have to compute my verification key myself. It's exactly the equivalent of you knowing not to trust the Nigerian prince mail, knowing not to share your private key.
Tell us a little bit more about yourself, Marcin. Where you come from? Where do you go? What do you do around these parts of Matter Labs?
Look, listeners probably did not show up here to talk about where did I come from. Let's talk a little bit more. Because that's the boring thing. It's not, historical figures or anything like that. I'm looking for something that goes a little bit deeper technically, that allows me to learn something new. Not crazy deep. I mean, sure, there are podcasts that will go in and explain you details of elastic curves and whatnot. But here, I'm looking more for something that is deeper than, a counter.sol example. Something that will explain you how pieces of blockchains, if we depend on how they work, but not all the way down. The good example will be if you compare it to a car. If most people are driving, they know that there's the engine. In this podcast, explaining a little bit more how the engine works, but not getting into the very nitty-gritty details. So
Yeah.
hopefully the questions will be good. Hopefully I'll be able to spark this piece of excitement in your eyes. The same thing as you said, Krinza, in our first meeting. Yes, it started with let's talk about something, and then end up with 1 hour, 20 minutes of discussion about different things. Both me showing you the things that we could do on the blockchain that we're not doing today, and pieces of how blockchains work and how can we repurpose this to different use cases, different approaches. Because one thing that personally, I would say, hurts/disappoints me is blockchain is a super powerful thing. The concept of distributed ledger, which works where trust is based on math rather than social trust, is extremely powerful concept, especially in many real life use cases. At the same time, today we're just scratching the surface. We're using it for a very simple use case.
Hmm.
For me, the comparison is blockchain is like a microscope, and we're using it to hammer nails into the walls. Heavy object, it puts hammer into it puts the nail into the wall, but that's not what microscope can do. And the thing is that most of today's use cases, we'll talk probably about some of them, like NFTs, FTs, token flipping back and forth. We're doing financial system, that's fine, but this is just the nail. And I want to talk about a lot of other use cases where microscope can be used for. But it will all depend on your questions. So just to put a little bit of a pressure, I hope you have amazing questions. Let's go.
I guess one of the first things that maybe we can start off with, like, talking about how you want to like learn something new. It doesn't have to be super deep. And I think this is just more maybe just like a fun fact and can help expand people's understanding of ZK. But there's this book that's out there called Zero Knowledge Proofs. Explain to me like I'm five. And not a lot of people know this, but you are actually the author and creator and the brain behind that book. So tell us a little bit about like what made you end up wanting to create that book and go down that route of making something like so simple but so popular.
So part of the reason why I came to Matter Labs is to learn about zero knowledge. Right? And my thinking before joining the company was fantastic. I'm going to join there. I'll be able to get to the very bottom of everybody must be an expert. I joined the company. My first meeting, I meet with Ramon, and it turns out, no.
We are naming
Okay.
names.
Of course, Ramon hopefully is listening. I mean, this book was dedicated to him. He was my inspiration to kind of create that.
Okay.
But more seriously, my hope was really that, hey, everybody in Matter Labs must know ZK, like, it must be obvious, right? It turns out no. And it turns out only a subset of people do, partially because the learning curve is so steep. Right? And we've seen cases like this in the past. Before this, I was in AI, and like the same story. When AI was starting, everything that was out there was basically a research paper. If you ever read a good research paper, you know that one thing researchers are busy with is making sure that their words are sounding complex, even if the underlying things are not. Because that's why they are paid, right? So the problem is that when new area shows up, in this case, let's say ZK, most of the knowledge will be coming from papers, from research papers, from some kind of articles, which means that it will be very off-putting for people that are trying to get in. Because suddenly the first two sentences you read and be like, is this even English? Like, what do you mean that there is elliptic curve and I do a point? Like, oh, right? And there are no simple analogies. There are no simple kind of thinking boxes for you to be like, oh yeah, I don't need to know about this because only this and this is important. A great example, a great comparison actually, is if you think about electricity. Think about electricity a couple hundred years back, when it was created. It was all about like magnetism and things moving and electrons jumping in and out, like crazy. But in our day to day, what you care about is like, yes, you have a power plug, you should plug it in like this. Do not touch them with your fingers, but you can touch them like if your circuit breaker goes, you flip like that. Like these are the basic things that everybody knows how to use without needing to fully understand what's under the hood. And this is kind of the similar gap that we'll have to cover with ZK and with many other technologies. Right? A thing that's a couple years in front of ZK that you can observe right now is AI. When I started with AI, this was a little bit even before TensorFlow. People were using NumPy to multiply the matrices. Like the papers were full of like, yes, you're gonna take these matrices, you're gonna like do the following pandas operations on top of that, and off you go. Then came TensorFlow, then they came PyTorch, more and more libraries. Now people rarely would use even PyTorch, they would use existing set of weights, like in 2 or 3 lines, Hugging Face, whatnot, to get this going. Because we already created all those interfaces, people know how to use it. The same thing will happen with things like ZK, and it's our role to do some of these things. And kind of that's where the book starts. It's one of this tiny, tiny stone in this whole pile of stones that we have to build in order to make it more approachable to users.
I I think you bring up a great point of like ZK, like this book helps explain ZK, like our understanding of how electricity works in our walls and then we use it day to day. So I am really before I get to the like this next question, I just like a sidebar of like how important is it that people even understand like let's say the two audiences, developers and users, how important is it that they know what zk is and what it does behind the scenes when they're interacting with zk sync?
Again, coming back to the electricity, you might not care, most users should not care how power plant works, the same way how exactly the ZK works, but they know, do not put your finger, do not touch electricity with your finger, but you can put
Yeah.
a plug in it, right? I mean, for us it's obvious, but if you think about it from someone who's seeing for the first thing, it's like, okay, I can put this thing in, but I cannot put my finger in. Why?
Yeah.
Right? Like if I put something into water and I can put like that's safe, but why doing it? Like these are the basic concepts that are crucial to understand because you will hear, and here's the reason why, you will hear more and more people talking about, oh, it's safe because it's protected by ZK. And it's important that users have enough of vocabulary, enough of knowledge to ask the proper questions to understand whether it is actually secure by ZK or not. Because
Okay.
unfortunately, these things are complex. So even if you talk about zero-knowledge verification, zero-knowledge verification has these pieces. There's like the verification key, the public inputs. Maybe we're going to go into those things. And it's important thing for users to be like, okay, fine, but where is this verification key coming from? It's a similar concept to me, in real world, if I give you a padlock with a bunch of keys, your first question might be, Marcin, did you give me all the keys? And in the ZK, it's equivalent of like, I'm giving you a padlock and a key, and people should know that like, hey, how do I know that there are not many keys? Or how do I know that this padlock is even like locking? Your knowledge is this powerful technology, but it's important for people that are using it or are depending their security on it to know to ask the right questions. People already learned that when you have private and public keys, you should not be sharing the private key. That's why it's nicely known private key. Probably at the beginning, many people probably did. Before that, people receiving magic spam emails also learned the hard way that you should not be clicking on random links and putting your data, into the public. Imagine the first person that got the spam emails, like, wow, Nigerian prince is giving me all this money, must be fantastic. Now we think it's funny, and I agree it is funny, because we have all this experience. And my point is that we need to give this experience, explain this when it comes to ZK. It's our role, explain to the users. Because again, if I tell you, hey, this is the output of my proof, you can verify it. Here's the verification key. You'll be like, Marcin, but where did you get the verification key? I should not be accepting your verification key. I should compute it myself. Otherwise, I'd have no idea what you're giving me. This exact exchange, you asking me like, okay, wait, thank you for the proof, but I have to compute my verification key myself. That's exactly the equivalent of you knowing not to trust the Nigerian prince mail, knowing not to share your private key. We have to get out to people that they know what questions to ask. Otherwise, what will happen is there will be some very bad surprises that can put a big stain on ZK's technology. Now let's do a little bit of a technical learning curve. And by the way, to the listeners, this will be Braden and Krinza learning. So this will be me quizzing them a little bit. They are employees of MatterLab, so they totally know what ZK is, and they know what pieces to touch and what pieces to not touch. Can you give me like a half sentence? What is a zero knowledge proof for you?
For me, a zero knowledge proof is being able to prove something without revealing the full information that would prove it, I guess. Being able to prove my age without telling you my exact age.
I think for me, it's about coming up with a new mechanism that gives you a trustless way to prove something. I know there's math that is more secure than how humans coordinate in a global coordination network. And that's also one part of how blockchain works. But at the same time, I think there's value in math and how it works because of its deterministic nature. That kind of also gives us a trustless way to prove and verify something. So for me, ZKPs are basically that.
Wow, that went far deeper. Okay, so if you imagine those all those like Indiana Jones movies, right? They had all these things, all these like puzzles, whatnot. And my favorite moment was usually when they had something that's broken into 3 pieces. Think about like a cube or like a sphere. It's broken in 3 pieces, and then it clicked together, and like ta-da, the power was something. So the very much simplest way of thinking about ZK proof is, again, imagine this complex sphere. It's broken in 3 pieces. Now, me coming with ZK proof is 1 piece. That's what I bring to the table. The other 2 pieces is the verification key that we're going to discuss about in a second, and then the public input. And now we will explain all these 3 things in just a second. But the whole concept is have these 3 pieces, and then the concept of zero knowledge proof verification is like you put this sphere together, and if it like clicks, it's like, fantastic, this whole thing is correct. For example, if you say, hey, I want to verify that my age is under 18, whatnot, then the verification key is basically this logic. It's literally this piece of code that says user.age is smaller than 18 and some additional verifications. So you as a user should be able to, like you as a person observing this should be able to, like, okay, this is this code, let me just like squash it, and ta-da, you end up with 1 part of a sphere. The third part of a sphere is what we call the public inputs. And in this case, let's say, Braden, this will be your name and maybe your social ID or something like this, this unique identifier. So then we end up again with these 3 pieces, that there's the proof, there's the verification key, and then there's the public data. And here's why it's important, because look, if this verification key was different, right? If you did not check the verification key is correct, it might be a completely different code. It might be code that just returns true, right? So if I give you a proof and I give you a verification key, it would be like, and then you provide this public input and it clicks. You should be like, Marcin, where did you take the verification key from? Because if it's just saying true, then any input will click. The same thing with public input. Like, if you don't look what is in the public input, then you don't know what actually are you even verifying. That's why all these three pieces are crucial, right? And usually the way it works is that the person that has private information is the one who's able to come up with a proof. To create the proof piece, you need this private information. The other two parts, the public input and the verification key, should kind of be checked by the verifier, should be kind of almost provided by the verifier. No, because what zero knowledge is, it's a proof of computation, right? We're like, if we change subject for a second, hashing, regular hashing is kind of a compression of, lousy compression, like let's say a signature of a data, like compression of data into like one piece, just a fixed data. So what hashing is to data, and the idea is like if you change anything in the data, then the hash would change.
Yep.
The same kind of parallel is computation to zero knowledge proof. So if anything changes in the computation, suddenly the zero knowledge proof is different. Right?
Okay.
So, but again, proof is just one piece, but then you need this verification key, which is, let's call it hash of the source code. It's not, but for simplicity, that's a good approximation. Because then you know that, hey, whatever this proof was doing, it was actually like running these commands. Because remember, it's a proof of computation. You need to know what it was computing, right? It's equivalent of like this. Like imagine I'm telling you like, hey, Braden, I run a function. It said 15. You're like, Marcin, great, but what function?
Yeah.
Okay. When you hear it doesn't make sense. Marcin, you did not tell me what function you run. Like the answer 15 doesn't make any sense. So you need to kind of know, like, I'll be like, oh yeah, sure, this function. I'll be like, okay.
Cool.
Because the other way of thinking about this, right, is, and we'll see if this explanation helps or maybe not help, is you will hear the word circuits everywhere, right? You hear circuits. Now, where it's coming from? The whole concept is, the first thing that jumps into head when you think about circuit is basically like a white or green basically board with a bunch of resistors and things poking around. The whole concept being it's fixed. Like you print it, it's there, right? And then you can kind of give a signal and then see if the LED light shows up or not, or maybe there might be some additional outputs going on. But the whole concept is the circuit itself, you do it once, done. Then you give it to someone and someone can be like, oh, I'm going to put voltage here and here, now here and here. Like they can play with it, but they cannot change the circuit itself. And a similar concept is here where like when we talk about verification key, when we talk about the source code, this function, you can almost think about it as a circuit. Meaning we both want to verify your age. So we both agree that this is the function that we'll be running.
Okay, yeah.
Right? A great example would be like this function, because now we're going to go deeper. How do you verify the age? Right? So example would be like, okay, there is some payload with your actual date of birth that's signed by the government. Right? So it means that, hey, there's a payload that's signed by this well-known key that, let's say, US government has. So this verification of an age is going to do the following thing. It's going to take, let's say, your name, maybe some social ID. It's going to take the current time. So these will be the public inputs in there. And now in the code, we'll do something. And the private input will be this whole package signed by the government. And in the code, it will do like, hey, verify that this package is signed properly by this government ID. Check that the package actually contains your name and surname, so that you cannot pass like Krinza's package in there. Check that at least 18 years have passed since the date of birth to the current timestamp, and then kind of return true, or like just don't, like all of these could be things as assert. And that's kind of, we agree on this piece of code, and that's what we quote put on the circuit. Right? We basically like print it. We print it. And the cool thing is that this is not specific to you, Braden, right? Like Krinza can take the same circuit and put her data. I can put the same circuit and put my data, right? Like the code doesn't change. And now we kind of create a hash of this code. This will be exactly the verification key, kind of. We squeeze this circuit into like something tiny, right? And ta-da! Now you can create a proof and be like, Marcin, I create a proof. And by the way, you should check the verification key is correct. And here's my public input. And your public input will be like your name and let's say the current timestamp.
Okay.
And this thing that shows that, yes, this proof says that you run this circuit successfully on your data and it's finished. So I know, hey, this function finished. So he must have had a payload signed by the government that says that he's over 18 years old, because otherwise that circuit would have failed, right? The LED light would not have kind of come on.
Yeah. Yeah.
I think the essence of zero knowledge proofs and the conversation that we just had right now, it's very much visible the impact that this tech has to like a lot of everyday use cases as well, right? Like action as simple as checking someone's age or verifying someone's age, right? I want to understand, because we like in this space we hear a lot of people say that ZK is the end game, ZK is the end game. Why is everyone talking about this? Like, why is it so important? Or is there any reason to believe that future of blockchains just wouldn't have worked if it wasn't for ZK? Or is it still very much possible?
I have my personal list for my career of like 6 different moments in my careers where I was like, wow, that's magic. Number 6 was exactly when I learned how zero knowledge works and how you can actually align these points in this like perfect, let's say, quasi line on the elliptic curves, like just wow, the pairing works. And it's just the case that the easiest or most impactful application of ZK is happening on blockchains today, but they can live completely separate. Because the main thing to think about it is ZK allows you, again, here we just mentioned like, one verification of something, right? Like you did some computation and then you create a proof of that and you can verify the proof. Again, here this was just a simple check of, is he over 18?
Mm-hmm.
But the beautiful thing is that this could be a lot longer computation, right? He could be computing something that requires a lot more data, a lot more processing, etc., etc. A great example of that would be if you imagine, now we'll see how quickly this goes with the listeners. Now, if you imagine you combine this with things like Merkle trees, then you can end up in the following thing. Imagine Braden has a company that has, a lot of users, and each of these users have whatever, some amount of books, some amount of items that he bought from Braden.
Nice.
Now, the amazing thing is that if he publishes publicly the root hash of his data, then he can suddenly start generating proofs of things like, hey, I have over 1 million users. How does it work? The same thing. It's a function, right? The function checks that as a private input, it accepts all the users. It can check that they really do hash to the public root hash and check that their value is greater than 1 million. He can do things like, hey, I have 15 users that start with letter K. Same thing, it's a function. He can kind of prove that, show it to other people, show it to external parties without having to be like, okay, here are all my users. Right? So it's a really groundbreaking thing when it comes to proving to the outside world that something is happening within your company, within your business, without having to share all the data out there. And where the end game comes in, the verification. We've been talking here about like, putting these 3 pieces into one sphere, ta-da. This is also computation. And because this is also computation, it can be proven. So you can go deeper. So this means that now I can take proofs from Braden's company, from 50 other companies. I can verify them. And the act of this verification of 50 proofs can also be proven with one proof. Right? So now if I, let's say, go to the government, I'll be like, hey, government, this is a proof, single proof, that I've proven 10,000 companies, and these 10,000 companies have proven millions of their records. And all these things folded into one. So the same way how you can create a hash of a hash of a hash of a hash to kind of potentially hash exabytes and zettabytes and yottabytes of data, the same way you can use zero-knowledge proofs to prove almost infinite amount of computation. And the moment you think about this means that in a small amount of time, meaning how long it takes to verify a proof, and this is literally in a couple cases like milliseconds, you can verify the integrity of potentially absolutely huge amounts of computation.
On proof generation, right? And tell me if I'm wrong, but what I have seen so far is that the cost of proof generation is usually very high. Like when we are talking about like large set of datas and stuff, right? And because of that, we only generate proofs of things that are 100% needed in the dApp and not for everything or anything, right? Do you think that this is one of the limiting factors of why we haven't yet explored the possibilities of ZK apps? Like, what is the current state of ZK apps at this point? And like, if there is a direction where you see that, okay, at one point in longer term, the cost of proof generation will absolutely go down to zero, is there a world like where we're going to see every app being a ZK app?
Okay, it will not go to zero. It does drop drastically, right? And here the amount of progress is absolutely staggering. Like many people, it's currently the biggest blocker of this industry. Still, if you look on the things 3 years back, 2 years back, 1 year, it's like the progress is tremendous, right? From the combination of being able to do more work so from progress on the engineering side, where people are using more and more of GPUs, being able to compute more things in parallel, to progress of the research side. There are a lot of improvements. We were doing snarks, now we were doing starks. We were switching between different elliptic curves. We were switching between different fields. All of them designed to be faster, to be more optimal. Right? We're getting to the level where now, through some things like SP1, we will start to be able to almost prove Ethereum at the speed of Ethereum, which again in the past, like 2 years ago, it would be like weeks or months. Right? So this cost will definitely drop. And the thing is, it's not about it getting to zero. It's about it getting low enough that you don't mind. Right? The same way how you can think about, hey, 20 years ago, if you were writing a computer game, you were really worried about how much bytes of RAM you can use because you had to squeeze in 512 kilobytes of RAM. And now we're just laughing at that. The same story there, right? Those games did not kind of go to zero, but simply the progress of overall hardware and software made it so that it became like basically worth nothing or did not impede. And yes, I am sure that this will trigger more and more use cases of zero knowledge being used not only on the backend cohort, on the backend right now, where we use it to, in most scenarios, not really to do the privacy part, but to do it for the succinctness part. That's what we're using it in blockchain, right? We want to compress this computation while still being public. There will be more and more cases that will both apply it to the privacy level, both on the customer side, right? Probably Aztec and many other Polygon Mine and whatnot. Many of them are working on doing these customer front-end proofs that you're able to just send the proof itself rather than the data. And also, I hope that in many use cases also outside of blockchains.
Interesting. I mean, when people talk about ZK, the conversations are usually centered around two things, right? Scaling and privacy. But to zoom into the scaling part of things, right? A lot of confusion comes around with the terms horizontal versus vertical scaling, right? You're good with explaining stuff. So I'm just going to take this opportunity. Like, if you can break this down, what do people mean by horizontal scaling? Because I was reading this tweet which said that You know how internet scales by adding more hardware to handle like more users? This is exactly how horizontal scaling works in blockchains. But on a counter argument, in one of the panels that happened in DevConnect, and someone was saying that one of the biggest proposition of ZK at this point is that previously we couldn't use traditional Web2 scaling strategies in Web3 because it would reduce the number of nodes verifying each transactions, right? But with ZK, there is a way where now people can use the same Web2 scaling strategies that have allowed internet to scale to billions of users, right? So in your opinion, what is a good mental model for people to understand how internet has scaled so far and how to form an intuition around horizontal scaling in blockchains?
So one huge difference between Web 2 and Web 3 is trust. Here's what I mean. If you're a company, and let's say you have a server, classical thing is like you launch a website, you have a server, fantastic, data hits the server, blah, blah, blah. And then the server stops scaling. What you do is you put another server next to it. You shard the data. So users from A to M go to server 1. Users from M to Z go to server 2. By the way, don't do that. Hash their IDs and then assign it, but for simplicity. Then you implicitly trust these two servers because you are the one running them. Right? So if there's a query that hits the server 1 and needs to get some data from server 2, it just friendly asks, be like, hey, can you give me this row? And server 2 responds. And server 1 kind of never mistrusts the server 2. It assumes that, yeah, it's safe, let's go. And that's how the backbone of almost all the sharding happens today in Web 2. Right? You literally trust all the servers because you run them, or they're run by AWS or GCP somewhere, but you trust the data that comes back. Now, imagine the model where what happens if you didn't run all these servers, meaning some of the servers were run by people you don't know, you just met. Suddenly this becomes scary. If you try to suggest something like this in Web 2, they will just throw you out. It will be like, what the hell are you talking about? No. The security, like if you go to Google and be like, hey guys, can you run this Gmail shard? Like John here will be running it somewhere at home. Like, what are you even talking about? Like, no, right? But that's the problem we have in Web 3, where you kind of don't know who's running this data. So the big problem was that the moment, as you were saying, Krinza, the moment you try to apply the same rules of sharding in Web 3, this means you also have to shard your validator set. So if before you had 10,000 validators that were like processing this one shard, now that you have two shards, you have to be like, okay, I had 10,000 validators and I have two shards now, so I guess I have to somehow split them, right? Of course, you can be like, hey, all the validators have to run two shards. Okay, cool. But then when you scale it more, you end up with something where, hey, now all the validators have to run million shards, and then it collapses, right? So at one moment, you have to start cutting it. Now, the moment you cut it into pieces, you end up in a situation, let's say in the extreme, they have 1 million shards, and each shard is run by one validator. Right? So then you're like, shit, this is not a very secure system now because one validator, can just cheat and the whole system collapses. So usually people say like, okay, we're not going to scale so much. We're going to scale a little bit less. We're going to scale so that there's a critical mass of validators on each shard, 5, 10, 15, 20, and throw in some more economic security on top of that. What ZK allows you to do here is, remember that through these recursive proofs, you can very quickly prove that all the computations that someone did, all the state transitions that they did, all the transactions that they applied, were applied correctly. So now the beautiful thing is that maybe, Braden, you are the only one running shard number 72 for the last 1 hour, but, and you keep telling me, Marcin, the root hash of shard 72 is this.
72
cool,
locked
dude.
down.
I'll be like, cool, dude, but like proof. And the cool thing is you can give me this proof. I can verify it very quickly in comparison to, because alternative for me is to rerun all the transactions that Braden did. But for this, I not only need the CPU to rerun this, I also need the storage. And that's the killer. Because while rerunning them on CPU, I can do a bunch of things on GPU, whatnot, do some magic. Usually, we also do sharding because of state. Because there might be additional 30 gigabytes, 100 gigabytes of state that these accounts were operating over. And now me getting these 100 gigs from Braden is like, wow, and some more. So before that, this was hard, but now with ZK, I don't need to get this data. I don't need to rerun these 2 hours of computation. I just need to verify the proof, which can be, by the way, done even on the cheapest Raspberry Pi in seconds. Also on more powerful machines, it's like under a second, millisecond.
And
so now,
really quick, that's because you have the proof, the public data, and the verification key is why you could do that on a Raspberry Pi and not have to have all the state and stuff that you're talking about.
Perfect.
Okay.
And by the way, just to show you the example, what would be a public input and what would be the verification key? So verification key, again, will be, in this scenario, will be a hash, right? But a hash of what function? So here's the interesting thing. If you imagine what the public key would be. So the public key would be something like previous state and next state. Notice you don't even need to know, and this is the tricky thing, you don't even need to know which transactions, because what's in the function does something like this. Take a state, which is these 30 gigs that Braden knows, compute the hash, make sure the hash of a state is equal to the previous hash, then take a bunch of transactions. Again, they are private. I don't need to know what transactions they are. But for each transaction, verify the nonce, verify the signature, apply it properly. So do the whole EVM application, update the state, do it for all the transactions, and then at the end, compute the hash of all of state, make sure that this hash is equal to the final hash. This is the function. This is the computation.
Mm-hmm.
Literally, take the previous state, apply all the transactions, take the final state, and make sure that these two hashes are matching the public input.
Would you say, like, just to like connect for users too, like,
What?
would you say that this almost like accelerates the fraud-proof window? Most people know a lot about optimistic rollups; they're super familiar. Would you say like this verification of the function, running through like all the transactions, taking the initial state, having the end state, is almost like accelerating the 7-day fraud-proof window into a matter of hours, because instead of having to like recheck that, it's like all being functionally verified by math and being proven that this is the end state, and no longer having to have this like 7-day waiting period for people to check to make sure everything's going okay?
Optimistic approach is, by definition, is optimistic, and it's just a stepping stone until zero knowledge is more powerful, is faster, which I think it's happening right now.
Mm-hmm.
Okay? Because it doesn't even compare. Right? The way to think about it is like with zero knowledge proof, you guarantee by math that a bad state transition cannot be submitted, because it has to be proven, right? It's like you literally verify it. Whereas with optimistic, you put it there and you hope that you didn't have any bug, and if you do, then someone will come in and fix it. And usually, if you did something bad, and this is my biggest worry with all the optimistic approaches, then maybe their fraud proof will trigger. We don't know. It never triggered on mainnet. And then we don't know what's going to happen, because there will be a lot of rollbacks. There will be like a complete chaos.
Right.
The way I would compare it is like this. Imagine I say that my building is fireproof. Now, what I do with if I'm using zero knowledge proofs, what I'm literally doing is every block I put into my building, I have a blowtorch and I blow on it. Meaning I check for every block that is correct, that is really fireproof. I literally blow it and it doesn't burn. Okay, fantastic, then I put it on. Optimistic, we're just putting it and hoping that it won't burn.
Would you say that like optimistic is fire resistant and ZK is fireproof?
The problem is we don't know if it's fire resistant. Because we never
Okay.
tried to put a fire, we never tried to put a fire on it.
Okay.
What we say is that, don't worry, even if it's not fire resistant, there is this fire suppression system that will trigger and make sure the fire is off. But it's
we
going to
don't
trigger
know.
with a little bit of a delay, right? Because it takes a while for it to trigger, and we've never tested it in mainnet. So keep building.
I
And
think
hope
it's
it doesn't.
I think it's a marketing department who's trying to sell us something, and we have just bought it. We're just waiting for the incident to happen so that someone can act on that.
Yes, and this is my biggest worry, is that we simply never tested it in mainnet. We don't know what's going to happen. And I am very, very worried that if it does happen, even if this fire suppression system works, even if these fraud proofs work, the fact that almost by design they will work a couple hours later, that's how long it takes for these fraud proofs in case of optimistic systems to fully finish all the cycles and whatnot, half of the building will be on fire.
Right. What was I going to say? Oh, I was just going to say that although we are getting into the deepers of like where we see the superiority of ZK, we still have love for our OP builders out there. So this isn't stunning, but hopefully enlightening those out there.
Check your fire insurance.
Good one.
I'm serious. Look, and this is one kind of grief I have with, unfortunately, many companies, ours included, is on one side, the reason why we do blockchains and not SQL, right? Because hell, most of the things you can just slap in an SQL database and off you go. It's going to be faster, for sure. It's going to be easier to build. The reason why we do blockchains is exactly for these 99th percentile failures, errors, issues, right?
Yeah.
If you trust your provider, you don't need blockchain. You just put an SQL and off you go. Right? So it's our duty to make sure that the systems that we're building are really, in this case, fire resistant, are really at the top of the game. And what I've been noticing is over time, people are like, yeah, maybe the fire won't come, so maybe we don't. And it's faster to build. I agree. If you don't have to think about these things, it's faster to build. Hell, as I said, just slap in SQL. Forget the whole blockchain thing. Just do row by row. It's going to be quicker. But it will not come with this guarantee. And then when bad days come, then,
I think that's very similar to like the decentralization argument. People don't care until they care, until it matters. And so same thing with optimistic. Everything is great until it really matters that you need to prove everything. And same with decentralization. Doesn't matter. Maybe people don't care that things are decentralized until that day that all the main servers, centralized servers, are shut down, and then you're left with nothing. So
yes.
People
and the worst part,
think forward.
And the worst part is that if this day comes and you see who's been left standing, saying "I told you so" will be a very painful part, because the distraction will be so huge, right? That even if it's literally you being the only building left, when everything else was burned down. Okay, yes, you win, but the whole neighborhood is gone. That's the worry. That's my worry. And then you saying oh yeah, I told you so. It's okay, fine. It's yeah, your ego is booming, but the industry is gone, and many people are really, really screwed, right?
Yeah.
Yeah.
So it's better to be pushing right now, right? But at the same time, the marketing and whatnot is a different story. I would love for you folks to invite someone from Optimism and Arbitrum and grill them why they don't have zero knowledge proofs right now.
We would love that.
And not in the future, whatnot. I mean, right now.
Call them
right
up.
after this. Say that we have scaled Ethereum, we have scaled blockchains, which is ready to be used by masses. Do you think that the current state of ZK developer tooling is accessible enough for devs to even actually unlock this abundance of block space that we have right now. There are like a lot of L2s out there, right? That also means that we have a lot of block space. Do you think that developer adoption is something which is going to happen in the near future? Do you think that the tooling around ZK is readily accessible for builders to start using? Is there an ease of development, or is there an ease of deployment that we are seeing? Or are we still talking about, oh, everyone has to write circuits, everyone has to like learn the nitty gritties of how things work in the ZK space? Where are we at this point?
So two important things to remember is that one, today, most of developers using ZK will be protocol builders, right? So most of ZK today is built by protocols, let's say Matter Labs, whatnot. So we're both doing research on ZK and also use it at the same time. But I think we passed the kind of manual circuit creation phase right now, as amazing job from like RISC-0 and SP1. Now you're actually able to really take small and medium and large Rust programs if they fill some limitation, if they fit in the given limitations, and get them proven on your own, right? So this definitely opens up the area where you don't have to think about writing your code in circuit-specific language, but you can just take off-the-shelf Rust libraries, most of them off-the-shelf Rust libraries, and just implement your code there. Right? I tried it myself. It was really easy to use. It's fantastic because try writing a JSON parsing in Circum, right? You have to write it from scratch. In Rust, import Serde, off you go, right? So this really will accelerate these things. So even today, as I said, you can just write your Rust code, add 1 or 2 lines, for example, in SP1, add 1 or 2 lines to be like, okay, these will be my public inputs. Run the code, it will generate your verification key based on your source code, then it can generate the proof. It's still expensive these days, right? You still need a GPU to be able to verify something larger. To prove something larger. Verification is quick. But over time, again, these things, especially the work that Polygon Maiden is doing, so they are focusing more on doing it tiny proofs for tiny computations. So exactly this, are you under 18, free verifications, whatnot. I think this is just a matter of time. Now, the important thing is for us to start working, and by us I mean listeners here, and you too included. Don't think you're off the hook. Working on actual use cases, working on actually looking where we can hide some of the data, where we can remove some of the data and provide zero-knowledge proof instead. A great example, just to give you there, is imagine you wanted to do a quiz on chain, right? A simple quiz where if someone knows the answer, they provide this answer and they get whatever 1 ETH or something, they get some reward. If you try to do it today on chain, it's very non-trivial. Because look, even if you bid okay, you write a function, accept answer. Answer is a string parameter, fantastic. If you compare the answer right there in the code, people will just look at your code and be like, oh, the answer is foobar. Okay, fantastic. I'm just going to get the money. Okay, so it doesn't work. If you do okay, compare the hash of the answer to something, okay, now they don't know what the answer is. But the moment the first person submits the solution, they will be like, the answer is foobar. Fantastic. Off you go. So what you want, right, is you almost want to have this ability of having private inputs to your blockchain. Where you as if you think about normal programming, you have option of saying, this is a function is private, this function is public, whatnot. Imagine having something like this in Solidity. Where you could be like, no, this function, this method, this argument to this method is private now. And now you as a user, if you know the solution, you generate a proof that you know the solution. And you send just the proof on the other side, and the contract on chain is verifying. So this opens the whole area of completely new use cases, completely new scenarios that people can build on chain.
Mm-hmm.
Just one.
I think it's kind of like what Aztec is doing with private and public state, though, instead of the functions.
Yes. Yeah. No. So okay. In case of Aztec, they are going 3 steps ahead. They have a different language. They have Noir, which has all these things built in. Yes, they are doing fantastic work, very much ahead, like in a separate corner than everybody else. But I'm also a bit more pragmatic. Like many people are writing in Solidity.
Yeah.
So one of our jobs is to make sure that we can offer them a stepping stone rather than be like, hey, forget everything you've done. Let's build everything in the new language.
Yep.
I have a lot of questions to ask. Like just from this last bit, I have questions around alt VMs. I have questions around, again, like just exploring the developer ecosystem at this point, exploring how different protocols are approaching the tech itself, like where we can improve in terms of research, in terms of development side of things. But I don't think we have enough time. So any last Braden, if you have any last questions, I have a lot, but I'll keep it for the next episode. So, Marcin, just a heads
Yep.
up, we're gonna see you again.
I think the same thing. There's a lot. Once you start talking, you start opening up a multitude of other questions that we have. So we really appreciate your time today, Marcin, and just explaining things with us, talking with us, and help spreading the word of why ZK is the end game.
Okay, so last parting words. If you didn't listen to the whole podcast and you're like literally at the end and you want to get one single thing out of that, the TLDR is ZK is more than just a thing in the background. You can actually think about how you can apply it also to the apps, also to the different almost type of things that you can build on a blockchain that was not possible before. And whether you do it on ZK Sync, whether you do it with Noir, whether you do it with Cairo, whatnot, that's the detail. But the important thing is that it really opens up the new type of use cases for blockchains. So go play with it, go try it out, and then let's build something exciting.
I thought you were gonna say ZK is the end game, but I think this was a better version.
ZK is the end game is just a keyword, and this is more like showing what you can do with that, right?
Yeah.
Yeah. Thanks, Marcin, for coming on the show.
Yeah, and we didn't even talk about the exciting projects. So this was just the boring stuff. The next time, we're gonna talk about those like permissionless things and the offline ZK and anyways, too many things.
This is
I think
Marcin
Marcin should be. I think Marcin. We should just add Marcin as a co-host. Marcin, would you be down?
We need an AI of Marcin. We'll make a model
AI
of
agent.
AI Marcin, and you'll just be in here, and then that way you
Braden,
don't have
go
to.
for it. Braden, I had no idea such an AI expert. Go for it. I'll use my AI to verify your AI. So.
Thank you again, Marcin. We appreciate your time.
Thank you.